Next topic, electrical systems. So I know that in automotive program, you're taking an entire course on electrical systems. So this should be pretty easy. It should be pretty light for you, for sure. But we got to hit it for math as well. Here we go. I put this slide up to let you know what you can expect from me on tests or quizzes. These are the sample questions that are fair game. I'm pretty into this topic, so I tend to get a little carried away with the combined circuits because I think they're really cool. But this is more along the lines of what I will be asking you. So if I freak you out, don't worry. It's not too terrible. But I do want you to be able to do number 4. So first we're going to go back to Ohm's law, which is another triangle thing. Just like our force pressure area triangle, we can have voltage is equal to current times resistance, and we also have our power triangle. Power is equal to current times voltage. And you'll notice I'm using V for the voltage. E is totally acceptable as well. It depends on, what you learned growing up and where you're stealing your formula sheets from. So you'll see I have cut out a formula sheet with an E instead of a V, but they are interchangeable for me. So we're going to use that triangle formula, both the power one and the voltage one, to do some circuit analysis, which is super fun. Just revisiting some of the topics or content or ideas behind it. When we think of electricity, I just want you to think of electrons flowing through wires, and they're going to operate devices by going through those wires to those devices. I don't care about which way your current is flowing, conventional or whatever they call it, actual. We just want to get through these formulas. So current, we're going to represent that with the variable I. So I is always current, and it's always measured in amperes. Okay, so when we're calculating current or thinking about the concept of current, it's just charge flowing past a point in a certain amount of time. Voltage, V or E, and this is our electric force, the potential. So this is what our battery gives us, and it drops everywhere throughout a circuit. It gets back to 0 volts by the time you return to the battery. Resistance, at least, is an R, and it is measured in ohms, which is the only one that has a weird symbol. Volts are V, amps are A, ohms are omega. And that's where you dissipate that power, you dissipate voltage. Power is P, measured in watts, which are W. So this is how we measure the consumption of any kind of load. So you think of how hair dryers are rated by power, or bigger things are related by their power consumption. Our power that we use, our hydro, is measured in kilowatts and watts. And that's my last note too. If you have a non-standard unit, so a milliamp or a kilo ohm, in order to do math with them, please switch them back to the standard. So I want to see amps, volts, ohms, watts. On your formula sheet, you're going to get this circle, and it basically is taking those two triangles and combining them into one thing and telling you everything you need. So let's say I was looking for voltage, which they're calling E here. So I go to the quarter where I'm looking for it. So if I'm looking for voltage and I have power and resistance, here's the full formula. If I'm looking for voltage and I have power and current, here's the formula. If I'm looking for voltage and I have current and resistance, here's the formula. And that's how you're going to use it. It's really nice. It's easy. You don't have to derive any formulas yourself. You can just go straight to this, find exactly what you need. So let's use this and solve a problem. Reading through this question, we have a defective motor and the resistance value is too low. So we're going to have a resistance. I'm just going to highlight it. We're also given a voltage. So I'm going to write those down. R equals 0.72 ohms. Voltage equals 14.4 volts. Now let's get to the actual question. I see 15 amp fuse, but that's the fuse that's in the system. So I'm going to answer the second question first, how much current is being drawn by the motor. Then I'm going to compare it to the amp the ridge of the fuse that's in the system and see if the current is too high, in which case it will blow the fuse. So I'm going over to my little formula sheet here. I want to find current, so I'm looking around here, and I have resistance and voltage. My formula that has voltage and resistance and gives me current is up here. So here we go. I equals voltage divided by resistance. So the current that's going to be drawn by that defective motor is going to be increased, right? Less resistance, more current, and we're going to get 20 amps in the system. I've answered part 2. Now, if the fuse is only 15 amps, 20 amps is definitely greater than 15 amps. So the fuse will blow. This is a very similar question. We have a fuse in place. It should be 15 amps, but we've accidentally inserted a 5 amp fuse instead. Okay, what numbers are we given? We have a resistance in the headlight circuit of 2.13 ohms when we add them together, however they go together. We'll talk about that later. And we have a circuit voltage. So R equals 2.13 ohms. V equals 12 volts. And if we're talking about amperage, finding whether it's good, we're solving for current. So we're looking for I. All right, which one we're going to use? Looking for I, have V in our same one. 12 divided by 2.13, and that current is going to give us 5.6 amps. So there's the answer to 1. Actually, they didn't even ask us that. We just want to know if the circuit's going to operate if we accidentally put in a 5 amp fuse. Well, 5.6 amps is greater than 5 amps, so the circuit will not work. This question is comparing power for 2 different devices, appliances, on looks like an AC system and a DC system. So we want to find power in 2 situations. We have, for the first item, the electric saw, current of 3 amps, voltage of 120 volts AC. So we're going to do power, and we're going to look for the one that relates current and voltage. That's right here. There's our formula. Power is equal to the current, 3 amps, multiplied by the voltage. We're going to get 360, and the unit will be watts. Looking now at our windshield wiper motor on a vehicle. Same formula. Looking for power, given 18 amps and given a voltage of 12 volts. So in this case, much higher current, 18, much lower voltage, times 12, and we get 216 watts. So which one uses more power? We can say that the electric saw uses more power. Out of Ohm's law and over to circuit theory. Here we have a simple series circuit. And when I say series circuit, that means the electricity has only one path to flow. You don't split. If you took your finger and started here and went all the way around, you wouldn't need to pull out another finger or choose a path. There's only one choice around. There it is. Look at nice and glowing yellow. So usually when you're solving these, you're given some information. Often you're given source voltage. Let's say that's 12 volts. Just keep it easy. And then let's say these 3 resistors, which are jiggly jagglies. Could be light bulbs, could be some kind of motor, who knows. But we're going to assign them some random resistances. So I'm going to say 10, 20, 30. Always in ohms. And I'm just giving them numbers because it's easier to talk about. The properties when you have actual numbers in front of you. We already know that V is equal to IR. And we know V, we could find the current if we could find the total resistance too. So if we wanted to make this about the total circuit, we just put little t's there. That lets me know you're working with the total circuit resistance, current, and voltage. All right, so what do we need to know? We need to know how current behaves in a series circuit. First of all, we're going to look at each one. Current, the total current coming in right here in series, is always the same. So current is the same across every resistor. And we express that with this equality. No matter where you are, the current will be the same. It never splits, it never changes. The resistance in a series circuit is the sum of all the resistance in line. So the total resistance here is going to be R1 plus R2 plus R3. And if we want to use the numbers we assign, 10 plus 20 plus 30 equals 60 ohms. Voltage is going to drop differently across each resistor. So if you start with 12 volts here, the circuit theory says by the time you get back and you're coming, let's say randomly we're coming back in here, you should have 0 volts left. You should use up all your voltage across any resistance in the circuit. So our total voltage will also be a sum. The sum of the voltage dropped at resistor 1, at resistor 2, and at resistor 3. Okay. How can we figure that out? Well, we have to start by figuring always your stats for circuit solving, and we'll go over this a few times, especially when we get into the complex one. Always start by finding your total resistance. Use your total resistance to find your total current. Use your total current to figure other stuff out. Okay, so for this series circuit here, I know that the total resistance was 60. I know that the total voltage was 12, so I can start by finding IT, total current, and it's going to be 12 divided by 60, which is going to give me 0.2 amps. All equal, so everywhere in this circuit we have 0.2 amps flowing. And I can use that information to figure out the voltage drops at each resistor. So if I take V1, and we know that V equals IR, we're going to have our current, the same everywhere, times our first resistance. And that should give me 2 amps. V2 is going to be the current, the same everywhere, times the 20. That's going to give me 4 amps. What do you think V3 is going to be? 2 ways to go about it. You can calculate it the same way we just did, 0.2 times 30, which is going to give me 6 amps. Or what else do you know? You know that the total voltage has to be the sum of all 3. So if you know that the total voltage was 12, and you just found 2, and then you just found 4, what's this got to be? It's got to be 6 amps. And we'll use that a lot in combined circuits. Here's a couple of parallel circuits we can look at. And we see right away they're very different than series circuits because current has choices. So the little blue line here, our current, comes out happily. We can trace it with our finger and we get to a junction and the current is going to split. Some of the current will go down path 1, some of the current will go down path 2. It'll rejoin and be IT or the circuit current at the bottom, but between points A and B on this diagram, it has split. I mean, if we add the 2 currents together, it will still equal the total current, but it has split up. So already different. It's not the same everywhere. We know that the total current, when you're in the parallel branch, oops, apparently I'm adding the 2 first, then the 1, but that's same. Voltage also behaves differently in a parallel circuit. So whatever voltage comes in to the parallel branches. So let's call it VT for now, because in this circuit there's no other stuff to use up some of the voltage. So we're going to get full source voltage coming into junction A. But it doesn't change on either branch. Both branches see the full total. So if we make this 12, just to get an idea on it, the VT equals the voltage drop in path 1 equals the voltage drop in path 2. And we're going to have 0 volts at the bottom when we drop all of the volts across the parallel path. Resistance is totally weird. It has a horrible formula. That is 1 over RT equals 1 over R1 plus 1 over R2. And this formula, usually if we're in class and we all have our calculators, they'll show you a bunch of neat things you can do with buttons on your calculator that might look like this or this. But because we are remote, I'm not even going to go there. You're going to figure each chunk out and go from there. So let's assign some values. We're going to call this one 10 ohms. That's what R1 is. And we're going to call R2 20 ohms. Okay, so whenever we want to solve a circuit, we're going to always start by finding the circuit voltage. So that's our first step, just like it was last time. It's just more of a pain in the butt. So here we go. 1 over RT equals 1 over 10 plus 1 over 20. Now, I'm going to show you 2 ways for a 2-branch parallel circuit because there's an awesome cheat. 1 divided by 10 is 0.1. 1 divided by 20 is 0.05. So 1 over RT is equal to 0.15. How do I figure out what the total resistance is? You have to kind of reverse the operation. 1 divided by 0.15, and that's going to equal 6.6 continuing. I'm just going to call it 6.67 ohms. So gross, but that's just how it is. Now, if you have a 2-branch and only a 2-branch parallel circuit, you can cheat. Total resistance is equal to R1 times R2 divided by R1 plus R2. So looking at what they're telling me there, R1 times R2 would be 10 times 20, which equals 200. And R1 plus R2 would be 10 plus 20, which equals 30. And you basically are going to get exactly the same answer. So this only works for 2 branches, but it's a pretty sweet cheat. Okay, you find your RT, you're back to where you're going to go. You find your IT. Circuit current, the total current is going to be equal to the total voltage, the source voltage, divided by the total resistance. And that will work out to a nice 1.8 amps. And because that current splits in parallel, it's the thing we don't know in each branch. So that's the one we actually end up solving for, because we know that in each of these branches, because there's no other place to drop the voltage, each of these is going to drop 12 volts, an entire 12 volts on either side. So if we want to find I1, we're just going to take 12 volts and divide it by R1, which was 10 ohms. And that will give me 1.2 amps. Okay, what do I know? I can go 2 ways here too. I know that if I have 1.8 amps in the circuit and I used up 1.2 in this branch, branch 1 here, that means that what's left to go in the other branch? 1.8 minus 1.2, I2 equals 0.6 amps. Or if you're not comfortable with that, do it the same way we found the I1. 12 volts divided by 20 ohms, 0.6 amps. Both of those will give you the same answer. When I solve circuits, I love to set up a table. This question asked me to solve the circuit. So they want to know, it looks like we've added power in here too, the voltage, the current, the resistance, the power at every location in this entire circuit. But if you use a table, even if I'm only asking you for one little value, it always works out well. So we're going to fill in what we know. We know that the total voltage was 90. And we know that the resistance of R1 is 23, R2 is 14, and R3 is 5. And we see that this is a parallel circuit because when I get to this junction, my current needs to split. There's not one path, that means parallel. Okay, so the beauty of a table is that if you have everything except one space in a row or column, you have the math to find that. So when I look at the resistance row, I have 23, 14, 5, which means I know mathematically I have the ability to find RT. It's a 3-branch resistance, or sorry, circuit. So there's nothing fun that's going to happen. I have to do the entire math. There's no shortcut if there's more than 2 branches. Shortcutting a bit, but making sure you recognize if you add up those 3 fractions, you haven't found the total resistance, you've found the inverse of the total resistance. So I'm still here, which means that the total resistance is going to be equal to 3.18-ish ohms. And noticing that property, when you have parallel circuits, your total resistance tends to be lower than your individual resistances. Okay, I'm going to ignore power for now because it's kind of like a bonus line I'd put in. So let's pretend it's not part of our table. We'll fill it in after. I have a total voltage, a total resistance. So I have, once again, a table where I have 2 out of 3 in this first column. So I can find total current. IT equals VT divided by RT. That should give me about 28.3. Woo, I called it amps. 28.3 amps. Okay, so at this point, there's a lot of information missing, but now we have to use our smarts, our understanding of circuit theory. Can we find the current across R1, R2, R3 right now? No, because the current's going to split, and that split is going to be based on the size of the resistors. Current tends to like to go to the least resistance, so I expect to see the most current in the bottom branch where the resistance is the least, but I don't know the split yet. What I do know that is that voltage coming into a parallel branch, you're going to drop the same amount here. I have no other resistances in this circuit, so I'm going to drop all my voltage in this parallel, and I'm going to drop the same in each branch. Voltage in a parallel circuit is the same in each branch, the voltage drop. So I can put this information here. And knowing that current is equal to voltage divided by resistance, I can calculate each of those branch currents. I'm getting 3.9, 90 divided by 14, 6.4, and 90 divided by 5, not today in my head, is 18. And I see that's true. You know, R3 got the most current because it had the least resistance. Now, what can I check to see if I'm right? If I split the current in 3, it should add up to 28.3. 18 plus 6.4 plus 3.9 equals 28.3. It worked that time. Often it doesn't because of rounding. It's a little different, but yeah, it worked out fine. All right, now we need to find the power. And you have lots of options for finding the power from that formula sheet. I'm just going to use the simplest, which is P equals I times V. And I'm going to do 90 times 28.3, and that's going to give me 2547. 90 times 3.9 for R1 is going to give me 351 watts dropped at R1. 90 times 6.4 will give me 576 watts dropped or dissipated at R2 or consumed. And then for R3, 90 times 18 gives me 1620 watts. And what do we expect to see? Total these up and you should get the total power. So another property of power in parallel circuits. We're going to use the table again for this second example. I'm just going to ignore power like I did last time and deal with it after. Okay, we have 90 volts again. I'm not sure where I got these from. Our R1 resistance is going to be 5, then 13, then 12. Oop, and then I almost forgot, R4 is 96. So what do we have? If I put my finger down right here and trace around the circuit, I never branch. The current never branches, so this is a series circuit. So I know that I can just add all the resistances together to get RT. RT equals 5 plus 13 plus 12 plus 96, which gives me 116 ohms. And now I know this. If I know the voltage in the ohms, I can find the current. Total circuit current equals 90 divided by 116, so it's going to be a decimal. 0.78-ish amps, and it goes here. When you are, now circuit theory time, when you are in series, what do you know about the current? It's the same everywhere, so boom, you've got all your information. And in order to find the voltage drop at each resistor, you're just going to do V equals IR. I've done that math in each of the columns to create all these values. Once again, if I add them up, they should equal or be close to, I'll give the approximately equal to 90 volts. And if they're not, hopefully it's only because of rounding, not because of a mistake I've made. If I want to find the power at each, once again, I'm just going to be lazy, and I'm going to do P equals I times V. And here we go. It should hopefully come out to approximately equal to 70.2 when you add them all together. So that shows us that, once again, power is got that formula of addition. So PT equals P1 plus P2 and so on, no matter whether you're in series or you're in parallel. Now, if you check my numbers, you'll be like, you're off by 3 or 4 or 5. That's all because of rounding. So I went back and double checked. Just be careful, rounding really does change them, but the theory should be consistent. All right, let's take it to the car. So our automotive terms, which are basically the same, our source is our battery. We don't often see it in our diagrams. It's just coming in hot at all times or not hot on key on. That's our source. The load is the resistors. So the things that I was drawing like this have now become your actual wipers, your horns, your lights. We haven't really looked at a control, but that is a switch that'll allow you to turn the circuit on and off. Circuit protection device. We talked about it in Ohm's law, but didn't really draw it on there. That's if you throw a fuse. Oh my goodness, I can't remember what a circuit breaker looks like. I don't know. I'm making that up. A fuse or a circuit breaker in, so that you don't, in case of short, wreck everything in your circuit, especially if you're bringing in like electronics. You really want to protect those. And a complete path just means that the current is able to flow from your source through the load and back through. Instead of drawing it all the way around, we often draw the grounds like that, which means it's just going to take you right back up to that source. And our wiring diagrams tend to look different than our electrical schematics. We have these dotted lines that represent part of a component, hot at all times from our source, fuses, a bunch of other things on circuits. It's nice because they always label the color of your wires and the location of your pin and your connectors, so it's nice to make your way through these in theory. So let's make sure we remember how to identify parts of a schematic. So if I want to find the source, I see the word hot at all times. That means there's a battery up here somewhere. And we're doing the horn circuit. So where's the load for a horn circuit? We have a relay. And if I look down on the left side, I have some other stuff. I see a switch, which I'll come back to in a minute. But when I look over to the right is where I actually see my horns, my loads are here. When I look for my control, I'm going to go back to that switch. And that switch is going to activate, in a way, the relay here, which pulls another switch shut to activate your horns. Your protection, I gotta be circled in lava, a fuse. And your path we'll do in rainbow. Woo, that's a big rainbow. Comes from hot at all times, so this is going to be ugly because that's a big pen. Down through the relay. We split here. What type of circuit is that? And we go back to ground. Sometimes when I look at wiring diagrams, it's just easier for me to redraw them as a simple circuit, just to see what's going on. So I'm thinking about the horn circuit again, the path. I'm going to change my hot at all times at the top of the schematic here into a little battery. Ooh. And then I'm going to go, I'll put the fuse in, why not? And I'm going to go through a relay. I'm just going to represent the whole relay and the horn switch with one little switch because it's my simple circuit. And then I go along and I'm going to hit this point in the connector. And at that point, I'm splitting between my left horn, which will make a resistor, and my right horn. And then I come back to ground. So they're going to connect up and we don't have any more voltage drops all along. And there's the horn circuit. So it's very easy to see that it's a simple parallel circuit when I redraw it. Now let's think about troubleshooting. I know you've done this. Where can I look for problems? If the right horn doesn't work, I go over to the circuit. I mean, the left horn's working, so the problem can't be anywhere before this connector. Likewise, it can't be anywhere after the return to ground. So if the right horn doesn't work, the problem must be, you know, at the connector with the horn right here. Or on my simple circuit, the problem is somewhere in here. Left horn doesn't work, the problem must be down here. Down here. If both horns don't work, we've got lots of potential problems. And that opens up whether other components are working as well. So if both horns by themselves don't work, I would say you could have bad grounds or something along here where they match back up. They are two different grounds though, so that's out of the window. You can have a mistake in the horn relay. If nothing else is fused, it could be the horn fuse. You're looking in different places. It could be a loose connection up here to the relay, who knows? And likewise, if we have another component sharing fuse 23 not working, then I really am going to start looking at the fuse for that problem. Here's a fun one. What's the minimum resistance, maximum power of the horns in this circuit? Well, let's just say, I know it's usually higher, let's say battery voltage or the source voltage is 12 volts. What other information do we have? We have a 15 amp fuse. So that kind of holds us. So our resistances of our horns, and I'm just going to talk total resistance here, I'm not going to do individual horn resistances, would be found by doing R equals V over I equals 12 over 15. And that gives me a minimum resistance of 0.8 ohms for that. We can go higher, right? Because that'll just pull back the current, and that's fine. It's just I don't want my current to go above 15 amps, so I don't want to have a low resistance resulting in a higher current. For power, our power max is going to be, if we can just get right to that 15 amps without blowing anything, 12 times 15. Maximum power will be 180 watts. Lastly, we're just going to talk quickly about wire gauge. If you're rewiring something in your car, how to pick what size wire you should be using. They're going to have resistance naturally. So every wire, no, like copper wires, whatever, it still has internal resistance. So how do we reduce that internal resistance? By not using super long wires, if we can. Don't have extra wire all coiled up and tucked somewhere under the car. That's no good. And you can also use thicker wires. And when you use thicker wires, you have to remember, if you're talking about American wire gauge, I think that's what AWG stands for, that the lower number means up thickness. So 10 gauge is thicker than 14 gauge and so on and so forth. And that really just derived from they used to pull them through dies to kind of shave off wire size. So the smaller you needed the wire to be, the more you had to pull it through a die, so the higher the number was. The key point for this, because we're just going to look on a table, round up. You know, if the table has 15 feet and you have 14, don't choose the 12 feet on the table, choose the 15. Round up for current as well. So let's see a couple of examples. All right, so we're going to start in yellow. Here's what the table looks like. It's on your formula sheet. We're going to draw 20 amps, and we're going to use a 5-foot long wire. So what gauge wire should we use? So that's a question we're always asking. So amps are going down here. So I'm going to find my 20 amps. And then I'm going to go across for the gauge, and I find 5 feet. And I'm just going to figure out where those two intersect. So just going like this to read it, and I see that I should use 18 gauge wire. Number 2 in green. So we have a 12-foot wire. So I'm going across the top right now, and I see my choices are 10 feet or 15 feet. Like I said, always round up. You're on the side of caution. So we're going to use the 15 feet. And we need to carry 25 amps. Once again, for the amperage, we have 24 or 30. Don't choose 24. Don't be like, well, one was bigger. So choose the right answer will be to round both up. And we see where those two intersect. I'll just use the whole green. Will be at 10. So we're going to use a 10 gauge wire for that alternator. And that's it. That's all. It was a big, long thing, but I'm hoping you were able to fast forward through a lot because you knew it already. And next class, we will be talking about the super fun stuff, combined circuits, and a little more troubleshooting.